So the question is, where do we go to find out how to use an I2S peripheral with the Raspberry Pi Pico? So as I mentioned before, there's quite a lot on the internet. In the extras section of the Pico CSDK, there's some I2S libraries, and there's a lot of people building kind of MP3 players, that sort of thing. But I like the look of this by somebody who calls themselves in GitHub their Malakalypse. Sounds like a Pratchett character. And it's actually a guy called Daniel Collins, and he released this 2 years ago. And the description is full-featured I2S PIO. So the PIO, we'll need to get into that, but that's the kind of little state machines that that can almost run without interfering with the core processor of the Raspberry Pi Pico. So it's a good way of offloading some of the mechanics of I/O from the Pi Pico. And this is bidirectional, double buffered DMA support, intended to be used with all common codecs, but modular enough to support unidirectional DAC or ADC implementations. So this sounds perfect. Looking down, it's looking at the license. This is under a GPL3, a GNU General Public license. So respecting license is very important. My understanding of that license is that you can take the software, you can modify it, you can sell it, but you must make the source code available and also a copy of the license. So that's fine with me. If I end up with a product I can sell, fantastic, but I will respect the license and keep the software open source. So I'm going to investigate this. So first of all, I'm going to see if I can get Daniel Collins's code to compile. So we need to clone the repository. The important bit's this here, so copy that URL, clone it into here, git clone, and that URL, and then we will open Visual Studio. Open the folder, let it do its thing, and hit build, and see what it makes of that. Fantastic. So it builds straight out the box. So I'm going to breadboard up some hardware to test this. So I need to know which pins to use. So looking at Daniel's code, this is the significant line, the config here, which populates this structure. The structure is actually in the header file, but I've copied it here for reference. And the various parameters are: this is the sample rate, 48 kilohertz. This is the serial clock multiplier. So this is the frequency of the serial clock as a multiple of the BCK, the bit clock. Bit depth, that's 32 bits per sample. Which GPIO pin is used as the serial clock? So this is GPIO 10. Which is the data out and data in? So they're GPIO 6 and 7 respectively. And this one he calls the clock pin base. And he mentions in his notes that the GPIO pinouts need to be contiguous. So they need to be, and this is a restriction of the PIO, that the various pins of a state machine need to be next to each other for hardware reasons. And so he calls this the clock pin base, and this is actually the bit clock. So that's GPIO 8, which means that the left-right clock will be GPIO 9. and the last boolean is whether the serial clock is enabled or not. And as we saw in that hardware example, it's possible for some devices to not rely on an external serial clock. They can run an internal phase locked loop and derive their timing from the bit clock, but in these particular chips that I'm going to use the serial clock, so I've enabled that. So my reading of Daniel's code these are the pins that he's used. So data out, data in, the bit clock, the left right clock, and the serial clock. I see no reason to change those pin assignments because I'm not using the Pico for anything else, so those are as good as anything. When powered by USB, you've got a handy 5-volt out on the V-bus, and you've got, via the internal regulator, 3.3 volts out on that pin 36 there. So looking at the other devices, you parallel up the serial clock, the bit clock, the left-right clock, and then the PCM 5100 takes the data in, and the 1808 will take the data out. Really quite straightforward. There's a number of capacitors here, kind of charge pump capacitors, that sort of thing. It's got three, in the specimen layout, it's got three 3.3 volt rails, but I'll just connect those together. It's got some control signals. This is de-emphasis, which you set low to turn it off. This is the filter, which you set low to for normal latency, and this is the format, which you set low for I2S. And this one is soft mute, and it needs to be set high, otherwise it will mute the output, which is not something we want. And I'm only just going to take the left out from this. And on the 1808, again, as I say, parallel everything up, the bit clock, the left-right clock, the serial clock, all paralleled up, and then this one takes the data out, and it's data out because you're taking audio in, so it's data out to the controlling device. So here again there are some control signals. Format, you set low for I2S, and the mode, it can either be a principal or a helper device, so it's either the one that's in control, the controller, or it's the one that's being controlled, and by setting them both low, this is the one that's being controlled, so it's taking its serial clock from elsewhere. It's not expecting to drive it. And I'll probably just connect the left and right inputs together so that they all take the same signal, and we've got a 3.3 volt in, ground obviously, and a 5 volt. So I'm going to patch these all together on some breadboard, and we'll see how that looks. And here it is. So this is the 5100 in here, and this is the 1808. I've got audio in here, and I'm connecting left and right signals together. There is, you probably can't see it, but there's a little capacitor in there to just for some DC blocking, and then this is the out from the 5100 coming out to this socket, and the rest is exactly as per those example circuits. So these are the signals out from the Raspberry Pi Pico, and if you can just about make up, they're all kind of paralleled across, apart from data out goes to data in, and data in comes from data out, and then there's a sprinkling of capacitors, various things tied to ground. I'm picking up the ground from the Pico and the 3.3 volts, and this is the 5 volt across to the 1808, and that's about it. So we'll plug that in and
see if it works.
This is the input waveform. It's something approximating a sine wave. It comes out of the fold output from braids, so it's not a perfect sine wave, a little bit of a peak in the middle. And this is the output of Daniel Collins's code. And to all intents and purposes, that looks identical to me, and it certainly doesn't have those kind of jagged edges that we got with the PCM audio output from the Pico. So yeah, quite pleased with that.